Okay, let's go over a couple more questions. The first question is, which of the following best represents a carbon-chlorine bond in methyl chloride? So hopefully you can see all they're asking is what's electrophilic, what's nucleophilic. So you have to know how the electronegativity uh, difference is. So obviously chlorine is more electronegative. That should be the one that goes with the negative charge. Carbon should be the one with the positive charge, and so a delta positive on carbon and a delta negative for the partial negative and the partial positive charge is what you want to go with. So choice 1 is the correct answer. You cannot have the opposite polarity, which is what is shown in 2. You cannot obviously have two positive charges or two negative charges next to each other. The last one shows you a purely ionic bond, which basically means that the chlorine has left. And the carbon-chlorine bond is a polar covalent bond, not an ionic bond like a sodium chloride type of a situation. So next question is, provide a detailed stepwise mechanism for the reaction below. So they're basically asking you, to push some electrons now. In this case, even though they say stepwise, they basically want you to show how the electrons are moving. And so hopefully you can see that the bromine is going to be the delta negative, carbon is going to be the delta positive, and the nucleophile is going to attack. Now, as you know, that primary carbocations are not very stable in this particular case as the attack occurs, and we'll learn more about that in chapter 11. But in this particular case, all you got to show is how the electrons move. So the CN attacks, the Br leaves, and you end up with the given product. Now, next question is, for the following alkanes undergoing bromination, identify the number of monobrominated isomeric substances. Monobrominated just means that you should put one bromine atom as your final product. So of course, these are both alkane alike, and so the reaction is going to go through a free radical reaction. So when you treat this with Br2 and H nu as light, HBr will be generated just the same way as we did in class for methane. You can treat any alkane or cycloalkane for that matter to go through that reaction. Notice in the first case, all of your carbons are exactly the same. These are all equivalent. So if you wanted to just replace any one hydrogen, it can go to any of those 5 positions, and for that matter, you would say that there will be only one monobrominated substance. On the other hand, when you're looking at the second compound, you can have a monobromination at any of these 4 methyl groups, or you can use the CH2s within the ring. Notice you won't be able to use these 2 carbon atoms because they do not contain a hydrogen. It's a carbon bond, and you can't just remove a methyl group. It requires a great amount of energy to do that. So this can go through essentially monobromination can take place either at the terminal methyl groups. Those are the 4 locations, but they are all going to be identical. Or you can do that incorporating the ones in the ring. So there are 2 kinds of positions. So if somebody asks you how many would be present in, let's say you have cyclopentane and maybe there is a methyl group, and somebody asks you, you have to carry out a monobromination, how many isomeric products would you obtain? Realize you have a methyl over here, you have one hydrogen over here, which can be replaced. These 2 centers within the ring and these 2 centers within the ring are identical, so there will be essentially 4 such locations where the reaction could take place. Likewise, if you had a cyclobutane with a methyl, that would mean these 2 positions are identical. This is one, this is hydrogen, and then a methyl, of course. So again, there'll be 4 positions in that case. So depending on what molecule you have, what kind of symmetry guideline we have for that molecule, you can make your call, replacing just one hydrogen at a time to get to the final answer. Okay, let's take a look at some more. The question is upon chlorination of 2,2-dimethylbutane, how many monochlorination products are possible? So this is similar to what we just discussed. We have 2,2-dimethylbutane. So butane means 4 carbons. Second position has a methyl group, and you want to put a chlorine atom. So you can have a chlorine at one of these terminal methyl groups, or you can have it at a CH2, or you can have that at the final one. So there are basically 3 different kind of monochlorination um, products which can be seen. And so again, maybe let's utilize a different method to show that, maybe a triangle or something to show that that's going to be different. All right, which of the following is not a radical? So a radical needs to have an odd number of electrons. So notice we do have an odd number of electrons, 7 electrons here. We have an odd number for the oxygen. We have that for the case of carbon as well as boron. The only one with everything paired is the hydride, so that is not a radical, that is an anion. Okay. When 1133 tetramethyl cyclobutane is brominated at 125 degrees Celsius, the relative reactivity is approximately 1 to 82 to 1600. So seems like the tertiary hydrogens are going to have the highest reactivity at 1600. The question is, estimate the amount of the primary monobromide product among all the monobromination products. So you're given that you have cyclobutane, you're given that you have tetramethyl, so 1133, let's say this is 1, this is 2, this is 3, and this is 4. So this is being subjected to bromination. And you have primary centers, which are here, 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 and here. So total, there are 12 hydrogens, which are primary in nature. There are secondary carbons, which are at position 2 and position 4. So there are overall 4 secondary hydrogens that could be replaced. So one could say that the number of primary centers are 3 times the number of secondary centers. You have to estimate the amount of the primary monobromide product among all monobromination products. So this really is a math problem. I mean, you have to think about what is the probability that the 12 primary centers are going to get generated, and what is the probability out of all the probability of all kinds of bromination. So you're just going to simply say that since the probability of getting a primary center that is at 1, and there are 12 such hydrogens, so the probability is 12 times 1, because that will give you the ratio, divided by the total, so 12 times 1 for the primary centers, and you'll do the same thing for the secondary centers as well. If they were tertiary, then you would do the same thing for the tertiary, but in this case there isn't. So we're simply going to say there are 4 secondary centers, so 4 times 82, and it's a percent. So the number that we get at the end of the day, that will be a small number, which we are going to write as a percent. So you'll multiply that by 100. So that number will be 12 divided by 12 plus 8, 328, or you can say 12 divided by 340 times 100 to denote the percent, of course. We're just expressing it as a percent. So you can say 12 divided by 3.4. So that should be 3 point something. Oh, there is an answer, 3.5%, and that should be your choice. Okay. All right, let's go forward. The last question here is that you have iodine azide, and that adds to isobutylene. You can call that isobutene, nothing fancy about that. Um, that's isobutene. And they have told you that you have to use that, and the way it adds up is in this manner. Which group is the electrophilic group to which the pi bond donates electrons? So they're asking essentially how the electrons are going to move, and then they're asking how do you know that? And then it also asks you, do these results fit the electronegativity pattern for the electrophilic addition reactions? Explain. That's what they want you to do. So of course your double bond is your nucleophile, and so the way the reaction will proceed is, the way you can envision this is that the pi system is going to pick the iodine, and iodine is going to essentially let the azide anion go as N3 negative. Between nitrogen and iodine, you should envision down the group electronegativity decreases. Nitrogen has electronegativity of about 3.1 ish or so, iodine much lesser at 2.5. So my arrow didn't go the way I wanted it to go. One more time. Better. Okay. Sometimes it's difficult to draw with this, with the finger. All right. So I have here the iodine, which is going to add according to the Markovnikov rule. So that's going to be picked up by the terminal position, and the carbocation is going to go at the tertiary center, which is where the N3 negative is going to attack, and you're going to end up with the product. Notice the positive charge that you're getting on that nitrogen is only because the central nitrogen is making 4 bonds, so it is specific to that particular atom. Overall, azide does have a negative charge, so that's why we say. So the answer, where it says, how do you know? Well, we know because of the difference in electronegativity. Iodine is expected to have a much lesser electronegativity as compared to the nitrogen, which is why the bond breaks the way it does. And do these results fit the electronegativity? Yes, they do. They do. And it does follow the Markovnikov rule as well. Okay, I think that is it for now.